It's also a great pleasure for me to be here and to chair also the session. I have been a postdoc with Peter, and I will say a bit more at the conference dinner. So the first speaker is Jeff Wu. He was a former student of Peter quite a while ago. And perhaps inspired by Peter, Jeff has worked on an extraordinary broad spectrum of problems. And Jeff, he will talk today about the new Gaussian process model. Please, the floor is yours.
Okay, thank you. I think I was number 16 of Peter's student. I remember there was another celebration. I pointed out to Jianqing, he was 32, was the power of 2, I believe. Today is 35. In 1973, I came from Taiwan with an undergraduate degree, and the education background there was mostly memorization and competition examination. I came to Berkeley. The 3 to 4 years, counting the lectureship, really transformed my scholarly outlook and my life. I was very lucky to have learned from a group of masters. And the last of the group is my teacher, Bdrygp. Okay, so
you must have learned a lot from his mistakes that he used to make. He always reminds me that.
Okay, so this work is joined with Liang Ding, used to be my visiting postdoc, Simon Mack, now in the audience, and his assistant professor Duke. Anytime I run into problems, Simon will come to my rescue. Okay. Or this way. Okay, so what is science-guided statistical learning? Okay, so say engineer or scientist will give or have some idea about scientific models, some empirical evidence, mostly experimental, but sometimes observational, field observation, like in geology. And also they know the governing mechanism. So they give the data to the data scientists. But this data scientist, before he or she was enlightened, would just do, all the stuff we know, learning, computation, algorithm, data visualization, and then send the result back. But you can see the engineer was not very happy. The result make no scientific sense. Prediction too uncertain. I should point out, usually statisticians like to say mean square error prediction, but there's another thing very important is if your result make no sense, which is worse. There's a capital crime. That's even worse. Okay, so now, so you complain that the analysis is disconnected. Okay, so, sorry. So now the scientists use to incorporate the scientific knowledge and they get better prediction and better interpretation. You can see that the engineer is more happy. Okay, computer experiment, meaning experiment on computer. Since Fisher's time, and also most of my career until I moved to Georgia Tech was on physical experiments. Most of the masters we know from Fisher, Yates, Finney, George Box, and so forth. They were physical experiments, agricultural, chemical engineering, say manufacturing or Taguchi. Okay, but a lot of things are done on computer. For example, the aerospace, and let me see the pointer. Yeah. Okay. The aerospace, and another one is say in cosmology. So a lot of computation. Usually the computation would take a lot of time. Okay. So now I'm using an example based on the joint work my group with the aerospace group at Georgia Tech. So this actually is one part of called injector design before combustion, before ignition. Okay. So here you have, I show you this, I won't have time to explain all the details. So This injector geometry, 5 parameters, okay, like length, width inside the injector. And when you inject the liquid oxygen to be mixed with the blue one is the fuel inside the injector. You want to get a good mixing. A good mixing will lead to good combustion. And that's very important. The good combustion, otherwise you can have some problem. So there are 5 parameters. So this is based on the large eddy simulation. Large eddy actually is not the most expensive one. I'll get to that later. Large eddy in this case would be 1 run, 6 weeks, I believe. The number is there. Okay. So this is very, very large computation. Okay. So in the rocket engine design, we talk about only the injector, not the rocket. Okay. The injector itself is 14 days per run using large eddy. Large meaning large scale. Small scale will be even more complicated, but I won't have time to get into it. Small scale, much more reliable, will take a lot of time. And for military grade, had to be small scale. Okay. So how to explore the 5D design space? By simulation alone, because they'll be much cheaper. Sorry, this simulation is a finite element of finite volume simulation. Will require about 1,000 runs. So what one can do, and even the aerospace people, actually they knew about it for a long time before Kriging, because in aerospace, you know that you cannot run prototype would take a lot of time. So even 30 years ago, they would do these kind of things, although they didn't use the statistical work like Kriging and certainly computation. So emulation would be using surrogate model. There are other ways. I'll get to that later. So for example, if I have 3 different geometries, a different shape, and so, well, there are more. Suppose there are different, each geometry I have a few runs, it's very expensive. Then I can fit using Kriging to fit. And there's one step we didn't explain is that a new geometry may be different from the other geometry. So there's another technical work, mostly in aerospace engineering, how to combine all those and do a lot of work into a new geometry and you do prediction. Okay, so that's the, okay, now, so this is, let me show you that. Oh, this one should have the animation. Test it. Okay, fine. So on the upper one be the expensive simulation, numerical simulation. The low one is the one we build up in the statistical algebra tab. Much, much faster. Okay, you can see they are pretty close. Now, there are several papers I probably refer to, one in JASA. Whenever it's statistical paper, we are the first author. Whenever it's engineering paper, the first author. And this in AIAA, this one. So this is actually to using the emulation, which is much faster to emulate for a new geometry. Apart from one small part, it mimics very well. I mean, there has another story. We had to go to a lot of aerospace, but I won't do that. That how to rectify that. That can be done too. Again, using engineering and statistics. Okay, so a very brief on Gaussian process that we input, okay, say in the D space, and we have n points. That means we run n simulation, numerical simulation, and we get outputs. So using computer code, we want to predict and quantify uncertainty on a new code evaluation. New one will be denoted by X new. Okay, so what we do, and this is standard one at this moment, that we assign to F is unknown, a prior stochastic process, a structure. They can capture our prior belief on the unknown function. then condition on whatever data we have, we can calculate posterior, and that will give us a lot of things. Okay, so so this is a usual Gaussian process with the mean function, which is expectation of fx a random function, then covariance function between any two input point x1, x2, called kx1, x2. But we also point out that we should also look at just the variance. Okay, so these have been used a lot. So this is just a review that if I have one datum, then this is the posterior, 2, 3, 4, and so forth. The nice thing about GP is different from the way numerical people do. Actually, the numerical in finite element, in numerical mathematics, they done this, but using their methods. The way they handle stochastic is not as good as in statistics. I mean, at the beginning, there were a lot of argument between the two communities, and I was involved too. Now it's accepted because we have demonstrated a lot of work like calibration. This don't might work today. It's a very important scientific problem they cannot handle. It's an inverse, it's a special kind of inverse problem they cannot handle. We can handle very well because we can use, again, very clever use of Gaussian process and do that. Okay, so you can predict the new point. And then you also get, so this is the formula for the mean function. It's a standard one in textbook and also a variance. So that is a variance and that gives you the uncertainty. So that's a nice thing about using statistical approach to such problem, which is widespread in science and engineering and posterior. Okay, so in practice, say mean function, usually choose a constant unless you have some knowledge, then you can choose a linear function that capture a trend. That part is easy. For the covariance function, for this paper, we use the 1D and we extend to high D later using Matém function. And the index nu is usually multiple or half. Half is most common. And the omega, there's another parameter there that can be tuned from data that would capture how wiggly the actual process is. Okay. So, and then the nu actually capture the smoothness of the sample parts, Then we can do high dimension using isotropic or product form. Okay, so here's a true story. This is what Georgia Tech, the ISYE, my stack group, and aerospace. So, for example, the earlier flow prediction from a sophisticated GP model, the one we developed, we use the aerospace people did 30 simulations, each one 2 weeks or 2 weeks. So you can imagine how long. After that, we run a GP. So that was very good. However, so the aerospace program manager liked it, but they said it's unrealistic in terms of physics. They want something not the large AD simulation, is another scale, the very fine scale. So they said, and this sounds ridiculous, well, if I do the highest fidelity, and that cannot be done even in Georgia Tech, had to be in a military computer because that would be a real weapon. The high accuracy, each run is 6 months. 6 months. Same with Prague Winnie, because one of my students, selling product to them, so I heard the same thing. So that's not realistic. But here's the best story is that we didn't get the grant renewed, but it's for political reason. Okay, as usual, it's not that we're better than the other, but we didn't. Okay, but we didn't stop here. We're thinking then from this point on, it's not a question of money or grant. It's we want to pursue intellectually something of interest because we have our other funding. We do whatever we dream. That is the following. So you look at this physical problem, there are other information on F that we have not used. If we can use this information, develop a new tool, new methodology, that again will save number of runs. For example, in dynamic system, you can see this one, the low boundary condition. And this is a very simple dropping, and there's a monotonicity constraint. Another one is a shape constraint. But we are going to get a boundary, the differential equation. Okay, so such information in each of the three cases come from scientific knowledge. Here's another one. This is a beam. Actually, this was used in my other paper with Simon Mack, Roshan, and other. This was more mechanical engineering that we submitted to Journal of Mechanical Design. So you can see this beam is fastened, say, on the wall, one side. So you have two variables, x1 and x2. Okay, but when you try to model that, you can put some boundary condition. Why? Because as you know that if the beam becomes really tiny, then the beam displacement will go to 0. Right? That's on the width. On the length, on the length, you go to 0 then. But when the width, the x2, it thick becomes super thick, then, I mean, asymptotic, relatively speaking, that displacement also 0. So that means we have these conditions. And so if we model the behavior of, well, there are also material properties I don't get into, so there are different kinds. Okay, so boundary conditions are often available from scientific model or physical consideration. So the next one is the one we work with aerospace, is using the Navier-Stokes equation. This actually was in a pioneering paper, someone called Pope. Navier-Stokes was well known, but using Navier-Stokes for the turbulence or by Pope in AIA, again, this was a historical paper. So this actually was in our JASA paper and also in the AI paper, but that's a different talk. So these very complex PDEs, the Navier-Stokes equations, is a kind of conservation or momentum of different mass and different things. Okay, so the solution is very time-consuming to solve. Okay, and another one is let's say viscosity. That you have on the left side you have say near zero viscosity, or on the right hand side it's incompressible. In either extreme, there is closed form solution. It's not. So that will give you the boundary condition. Okay. So what we want to do is this. We want to integrate the boundary condition directly, key thing, into the GP process. If you solve numerically, then impose the boundary. That's what numerical people do. That's clumsy and much slower. Okay, and also as a structure of a problem, it's not as nice. Why don't you have a GP that incorporate the boundary condition? So that's what we do. Okay, so if we do that, we can improve the prediction and the faster posterior contraction and also more interpretation, because the model itself already incorporates the physics or part of the physics, only the boundary. So then there's a computational efficiency issue, theoretical properties. For today's time, I would just outline some theoretical results, but computational also is a problem. It's in our quite a long paper. Okay, so boundary condition, we use Dirichlet boundary. Okay, and in this case, we only, the boundary, so we assume the boundary we left is 0, right 1. So therefore, side we only have x1 equals 0, x2 equals 0. Only this side boundary, not the other side, just for illustration. So here I had to use a notation. I is the index. So it's an index set of inputs with known left, 0 is left. boundaries. So in this case, the I0 is 1 and 2, variable 1, variable 2, both has left boundary condition. But on the right side, remember the other side, there's no boundary condition, so it's an empty set. Okay, so how do we build the boundary GP process? The mean is easy. So if mean function need to satisfy the boundary constraint, that's usually very easy to manipulate algebraically. More challenging or interesting is we need to impose, so is look here, this one. Okay, the last bullet, that we know that if there's a boundary condition, that means it's already fixed. Then the variance is 0. Okay, so that's a constraint on the variance, but it's building, okay? And then that means simple path will satisfy these constraints. Okay, so now once we explain it, it looks very simple. But this, I think, the first time people do that. Okay, you put mean is easy, is a variance and covariance. Okay, let's now use a very easy 1D, and we can extend it. The Matén covariance and nu equal half. Nu equal is very easy, very simple. Well, but you can show that actually for some differential operator, actually self-adjoint differential operator of certain kind, that this one, the Matén, is well known. That's why Matén is very, very powerful, very useful, especially when you try to model phenomenon that has a physical one. Usually people use Matén, not the power exponential, which is mathematically simple, but doesn't have the same physical interpretation. Okay, so it would satisfy the green function, this green function. Okay, so now the idea is that we can put constraints either on left or right or both. Okay, then the question is, once we put these constraints with Matén, can we get closed form of the kernel, the Matén kernel? The news is good, yes. So those are the solutions. Either you have boundary on both sides, first one, or boundary left, boundary right. And this is the shape of the boundary. Okay, it's very important, it's simple, but you need to close form, because if everything numerically solved, it's going to take forever. You can see at the end, the boundary is 0. Okay. Well, when we knew that's more than half, it's using a kernel convolution, basically. It's a kernel convolution. So from 1/2 to 3/2 and so forth. Okay, and you can do high dimension too. Okay, so it has closed form. That's a nice thing. It doesn't matter that with the iteration is messy, because it's computed, it can be computed. And with that convolution, actually it's very fast compute. Now for higher dimension, we can do a product. Okay, so let me now do a 3D example. So the 3D example, variable 1 and 3, left boundary, variable 2, right boundary, variable 3, both left and right, because it's in both set, index set. Okay, so now let's look at the first one. This is the form, explicit closed form for the first one, second one, third one. Okay. So putting everything together, so we sort of build up this. Remember, we still have subject deletion prior, whatever, yeah, Matén, but these are, as a first attempt to do that, it's good enough. Okay, it can solve many problems. Okay, so we do in the machinery now. We have a Gaussian process that incorporates the boundary condition. we had mean function, we had the covariance. And then the nice thing is now the posterior formula is the same because the general kriging is a GP process or whatever kind. You can just compute posterior. Okay, so that's a nice thing about this. It sounds very simple, but make it powerful. So there's no extra computational cost. It's the same kind of formula. Or the only difference is we have a new GP. Are we done? Well, almost. So we're going to show you, demonstrate that this does improve over no boundary. But there's another issue that we don't have time. We only show briefly that is, I don't know, Simon, this will be our second paper or part of first paper. It look very long already. That is, where do we choose points? It's very important. This is choosing point for computation. Like these red dots, where to choose point. It's an experimental design problem. And this is not very trivial. I think we only show you a little bit of that. So the one is a full grid design. You never do it. Full grid is too large. The one that's used a lot, actually this was pioneered by numerical people, not by us, called sparse grid design. And their idea came from numerical people know to build from the low dimension, the computation to high dimension. And the reason low dimension, high dimension had closed form iterative formula. And they've been good at that for more than 100 years. So my group, most people had to read their book, the one small book, other book, big book. I even ran a seminar, a no credit seminar just to know that. Don't Be in Shoes book that we read about 4 or 5 years ago. Okay, so the idea is to use smaller number of points to understand the low dimension feature. This is 2-dimensional, but it's actually for high dimensional. Okay. They add points. But they add point in a very specific way that I will never thought of because they know from the numerical side. If I add point this way, whatever being done will be incorporated in the larger one and not just repeat the computation. Okay. And then so this is called sparse grid. Script. Okay, so now I show you 2 theoretical results here. One is no misspecification. So here we have d dimension, d variables. Each variable has at least one boundary, either left or right. And smoothness, meaning the true f function is in the reproducing kernel Hilbert space generated by the boundary kernel. Okay, by the boundary kernel. Then, and the sparse grid. Then we get these convergence rate. Okay, it's pretty good, but I don't know how much improve over the no boundary. In the numerical, yes. If you have this question, someone will answer for me who is in the audience. So you always get your co-author who is younger, sharper, and know all detail to be there, and you say, oh, I don't know, I'm too old, and they will answer the question, okay? Next one is misspecification. This is very important, because what if the true function f is in a larger space, the zero boundary sober space of a certain kind, but important thing, the order of that is smaller than nu. Nu is the Matém function. Okay, so what you want to know is, that means my true function may be not in the reproducing kernel Hilbert space. This is actually more a very pessimistic one because Sobolev has a lot of functions that are unrealistic, too wild. But that's a way for us to gauge how much rate we lose, the rate of convergence. And then that's the result. So you see here, because S is smaller than nu, and you do the little algebra, this is a slightly slower rate than the previous one. The proof is quite involved. Is Ding Liang, the guy, the postdoc, he did that. It exploits the connection, mathematical connection between the boundary GP, our boundary GP, and the finite element interpolation. If you know those finite element interpolation, it's an interpolation, a lot of the formula they use. And these two, the interplay between the two in order to do that. So that's very elaborate. Okay, so prediction rate, the optimal rate in all these cases we lead to improved power, predictive power. Of course, the predictive power, there are a lot of contributing factors, but boundary information is key, if not the only one, but it's a new one, it's a new one. And the other one is in the paper, but not shown here. It has a quicker posterior contraction rate with the boundary. Actually, I was very excited. And I told them, this was actually 2020. Oh, I need to speak in the Bdrygp conference. I wanted something more mathematical. I don't do a lot of mathematical work. I want something mathematical and maybe deep. Okay, I don't know, but you can decide. Okay, and by 2021, we got. But then delayed to 2022 and result even better. Okay, so I'm quite happy to report the results here. Okay, actually another thing we do not say scalability is due to the design. Remember I said the sparse grid, you build the high dimensional structure from low dimension. That's the nice thing about. So you do need, for this work, for a lot of my work in the last 10 years, I need to know numerical mathematics and physical mathematics for my group in order to do this. So that's the okay. Another thing also, it's I think Ding Liang already got the result. It's, and this is amazing, the posterior distribution with sparse grid only, sparse grid, not general, can be computed in linear time. And the reason is, again, is the structural sparse grid, low to high. But it's not, it's easily said, but it's not easily done. Okay. So that's, I believe, I think probably we need to go to another paper to do all of that. Okay. Numerical example, I'll do it very fast. I think I have enough time. Okay, with 3 test functions. One is very, in the corner, is a corner peak. One is called product peak. That means it's a peak by taking product of different component dimension. This is called Rosenbrock. This field has a lot of testing function. Also in global optimization. Global optimization in this field are becoming closer and closer. Okay. And in some way, I would say they move toward us because we have developed a lot of new tools. And global optimization have been around for some time. Okay, so left is a full boundary. And this partial boundary you can see on our side, right? Okay, this side, not the other side. And there's no boundary. We want to see with and or without boundary, how much we gain. So you can see that no boundary is the red curve, not as good in terms of the log or the rate or the error approximation. And this is 10 dimension only. So the partial boundary and the full boundary do about the same. But now we choose 3 much more complicated functions. You can see the middle one has many peaks. And the right left is kind of very strange. Okay. And the left one is a 4 peaks. So now 30 dimension. And you can see that the full boundary is better than the partial boundary, except for Levy. I don't know why. Yeah, Simon probably know why. Another one is we compare the standard GP without boundary. You can see that those, you know GP process, you see this very standard one in that you have the confidence interval for each point. But you see the error rate is very large, right? The confidence interval is very large. But look at the bottom one with the boundary GP. The boundary GP, what's amazing is it fit very well, and you can see it's very tight, very little error. Because, but of course, this is still easier problem than the Navier-Stokes equation with boundary. But it shows it's very encouraging and very promising. So this, with the boundary, can greatly reduce the predictive uncertainty. Okay, conclusion. So science-guided statistical learning, this can be called statistical learning. It's a learning. Okay, if I write a grant proposal to Air Force, I wouldn't just call GP or whatever. I have to say statistical learning because then I can get funding, right? If I only say GP process, say, oh, GP process have been around for so many years now, I'm going to cut down your grant by half or something. But it's really learning, okay? Everything machine learning, all the buzzwords, okay? So the science-guided statistical learning is crucial for tackling modern scientific problems with limited data. I only gave you some example. We have done a lot more with my group of different people, and Roshan has his own group. The boundary GP provide a basic model for integrating data with boundary information, which is science, with provable error improvement that we are the theoretical rates. The future work would be, you see, remember, we only have very specific Dirichlet boundary that we can do the mathematics. We need to do a broader class and different boundary types. For example, we have only rectangular, but in a lot of work. So this will be something that Simon Mack will do. I don't do. Okay, thank you. And
thank you very much for this nice presentation. There have a bit time for questions, comments. Maybe the others on Zoom can hear you better.
Thanks for the very nice talk. What other kinds of information, science-driven information, can you incorporate into your prior other than this boundary? Values?
The general PD, there are a lot of things. You know, I take the standard one, boundary is one, and this one we do initial condition, forcing terms. That you do the physical, you have the forcing terms. And if I do time varying computation or combustion, yeah, we can. There are other types. So the field is very wide, I should say, very, very wide. Yeah, I only touch upon a specific type of boundary condition. Yeah, so and I can stand another minute if you have a question, and they would. Oh, sorry.
There is no extreme hurry. They're just preparing for the next talk. So if somebody else has a question or a comment, Peter?
Maybe only
the ones on Zoom.
yes. You said you only had 2 points to fix the boundary conditions?
No, I never said it. The
N
two,
equals 2.
the two computation was A4. That's crazy. No, it's not 2 points. We have a region is 0 to 1. 0 to 1. So rectangular region left is 0. Right is 1. Okay, we can change to other rectangular region. Or simple ones we can extend easily. But you more circular other we don't know. But some of these are doable. But it's important to, so if the boundary is a left or right for each variable.
Yeah, so just trying to get some intuition here, right? I mean, if you have knowledge about boundaries and you incorporate it into a prior, does it improve your estimation throughout or better at the boundaries?
Well, boundary is already 0, right?
No, but I mean, your function has to come down.
The reason is that the whole function being influenced by the boundary pull to 0, right? Pull to 0. So I already demonstrated that the error rate is actually better than without boundary. Another one we didn't say here is the posterior contraction faster, also faster.
But you had an example of equal to 30, and it seems like the improvement was throughout rather than at near, because my naive thing says, condition says, you have better performance near the boundaries to get closer and closer to the boundaries. And the prediction information performance near the middle may not be that much better.
Yeah, no, that makes sense. Remember, it's the boundary that make the difference. So near the boundary is kind of poor. Yeah, it is. It's fair.
Good. I think in view of time, let's thank first Jeff again for the very nice presentation. And our next speaker is